friends. Hi friends. My name is Lucy. I'm an educator at the Green Bank Observatory. I work on the 40-foot. I work a little bit on the 20-meter, but most of my job entails taking groups into the Green Bank Observatory, showing them around, introducing them to the wonders of the Green Bank Observatory and radio astronomy, what it means, what it does, why we do it. The fact that we are doing things other than looking for aliens, that's always a big question. But one of my duties is sometimes I will fill in for tour guides and give just general public tours. And if you were here in real life, here at the Green Bank Observatory, we would stick you on a tour, but we can't do that. So you're stuck with me in a slideshow. I'm going to attempt to share my screen. And somebody give me a thumbs up if you can see this. Great. So this is a beautiful picture of the GBT in fall. Fall is my second least favorite season because I get really bad allergies out here. But GBT, you guys have seen pictures of this before. Couple of intro etiquette things. Feel free to unmute yourself and ask me a question. I can't see the chat when I have this open, but I will try to I'll try to notice if somebody says something in the chat and answer that in real time. If I don't get to one of your questions, feel free to just interrupt me. I tend to ramble, especially when I'm not looking at real people's faces. Green Bank Observatory is a radio observatory. And you guys probably already know the answer to this question. So somebody write in the chat one reason why we do radio astronomy instead of just doing visible optical astronomy. What's one benefit to radio astronomy? And Will and Ryan and Jim, you guys are not allowed to answer this question. So one thing that helps, that we can learn, that's useful about radio astronomy. Maybe. Can be done from the ground. Very good. Resolution. Yep. You can observe during the day. Yeah, so that's really important. With optical astronomy, you have to wait until it's clear outside. You have to wait until it's nighttime. But with radio astronomy, you can observe 24/7. Right now, we've got, well, it's a little cloudy. I'm not sure if you can see that, but we're still doing observations. When it comes to really, really tiny millimeter length observations, you have to worry a little bit about the amount of water in the atmosphere. But other than that, weather and that sort of thing isn't really a problem. Can be done from the ground. Very good. So one of the reasons we don't do gamma ray or X-ray astronomy is because we have this thing called an atmosphere. Y'all have heard of this, right? We've got an atmosphere, we have an ionosphere, which is great because that blocks a lot of X-rays and gamma rays from reaching us on the ground. And that's good because gamma rays are what turned Bruce Banner into the Hulk, right? We don't want to be near those. However, if you want to do gamma ray or X-ray astronomy, where would you have to put your telescope? You'd have to put it in space. What is a telescope in space called? Someone write it in the chat. Something that's orbiting around Earth. It's a telescope. What do we call those? Satellites. Radio telescopes are not satellites. Please do not refer to them as satellites. Radio telescopes look sometimes like the satellite dishes that you or your neighbors might have to get dish TV or whatever, but those are called satellite dishes because they receive signals from satellites, not because they're satellites themselves. If you refer to any of my telescopes as a satellite, I will kick you off of this Zoom call. I don't know if I can do that, but I will. I'll figure out a way to do it. Less atmospheric extinction. Very good, Casey. Not blocked by the atmosphere. There are things that can't be seen by the naked eye. Very good, Max. So I have a pencil right here. Y'all have seen these before. You can write with them. Yeah. Now, if this pencil were just floating around in space, right, you wouldn't be able to see it. If I closed all of these windows, turned off all of these lights, turned off my computer, there was no optical lights in the room, you wouldn't be able to detect this pencil with your eyeballs. But, so if it's floating around in space, you're gonna have to wait for this pencil to either pass in front of something that gives off light, like a star, or wait for it to reflect light. And that's a lot of work, especially considering space is a whole bunch of nothing. So there's a whole bunch of stuff that we just can't see with our eyeballs, in the visible light spectrum. But with radio waves, we can see a lot more. Very good. Savannah got that one too. It's the coolest wavelength. That is true, both in a, like, it's cool because it's rad, and also because the temperatures have to be lower. Cryogenics. That was a cryogenics joke, and I don't see anybody laughing. Greater range of observation frequencies. Yes, very good. Savannah thinks I'm funny. Thank you. Very good. Okay, so one of the things that I didn't see anyone mention is that we can actually see farther into different places. So just like if there is a really foggy day outside, right? And you're trying to drive, you can't see anything. You can see maybe 2 feet in front of you, that's it. That's going to be a problem because those optical waves are really tiny and they're going to bounce off of all of those molecules. We live in this thing called a galaxy, which I'm sure you all have heard of. Galaxies are full of dust and gas, and you can ask Will more about that. All I know is that the galaxy has a whole bunch of stuff in it. And that becomes a problem for optical astronomers because there's a whole bunch of clouds in between them and what they want to see. Now, radio waves can see a little bit farther into really chock full of gas and dust places like the center of the Milky Way. So if you're trying to do Sagittarius A star research, you're going to want to do that in the optical wavelength, or sorry, in the radio wavelength, because optical wavelengths, you're not going to be able to penetrate as deep. I should not have used the word penetrate, I'm sorry. So Jay went over a lot of this, but I'm just going to go over some of the things that we have here at the Green Bank Observatory. This is the Jansky antenna, named after Carl Jansky, who discovered what he called star noise. And I'm going to pull up the chat again, because I have a question for you guys. Carl Jansky discovered 3 different sources of interference. He discovered thunderstorms that are far away. He discovered thunderstorms that are really close, and he figured out that thunderstorms could cause interference with these transatlantic lines that he wanted to build, or Bell Labs wanted to build. And then the third thing he discovered was what he ended up calling star noise, this mysterious background hissing. And there were 2 different ideas as to where this work was coming from. The first was the sun, and the second was the Milky Way. And we weren't sure whether or not this mysterious hissing noise was coming from the Milky Way or the sun. So somebody write in the chat how we could figure out which, using just this telescope, which can point pretty much along the horizon and that's it, how are we going to be able to differentiate or tell whether or not, like, which of those 2 sources the radio waves are coming from? Do it at night? Yeah, that's a good idea. Point outside the galactic plane. So see if it changes over the course of the day. Yeah, so he noticed that this noise was actually more, it was stronger during the day. It was. For about 6 months. And then what do you think happened? So Savannah, this instrument wasn't really technical enough to be able to point outside of or inside of the galactic plane. That's a good thought. So Carl Jansky was actually really lucky in that when he was doing his observations, there was a partial solar eclipse. And he noticed that when the moon blocked the sun for those couple minutes, he was able to take his data and nothing changed. So that was really helpful. And he also waited 6 months until we were on the other side of the sun and noticed that then the this star noise was brighter or louder during the nighttime. Very good. Here we have the Grote-Reber radio telescope built in his mom's backyard in Wheaton, Illinois. It was painted red, white, and blue in 1976 for the bicentennial. Grote-Reber is, from what I hear, he was a pretty interesting guy. Not sure if he would have liked his telescope being painted, but you never know. So this is some data from that telescope, and it's from 1943. You can see that along these like little, can you guys see my cursor or no? Give me a thumbs up if you can see it. Can you see my cursor? Yes, okay. So you can see November 21st, 1943, right here. See, this data is all from 1943, and you might be able to notice some interference going on here. All these little spiky marks are interference from cars that were turning on and off, from radio stations, all sorts of different things. So Grote-Reber actually wrote in his logbook that he needed to find a place where there were no cars starting to move his telescope to, and he ended up moving his telescope to the Green Bank Observatory. It's right outside the Science Center, actually. It's pretty cool. This is the Ewan Purcell horn antenna, discovered the 21 centimeter neutral hydrogen wave. It's pretty big. It looks like a cornucopia. I have had at least one child almost get stuck in it, so if you ever come here, don't climb in it. So we are in Pocahontas County, which is both the least densely populated county east of the Mississippi River and the highest in elevation county east of the Mississippi River. We're about right here in this sort of chicken wing looking county, and we did that on purpose. So if you have a higher elevation, that's going to reduce the amount of atmosphere degradation that you have. And we chose to be in the middle of nowhere for a couple reasons. The first is that engineers and astronomers don't like talking to people. And the second is that if you have more people, they're going to be using more technology. And more technology means more interference. More interference means worse data for us. So here's the National Radio Quiet Zone, 56 or 57. I think the FCC decided on or created this sort of jurisdiction. And basically what this means is if you want to build a radio station or a radar tower or anything that gives off radio signals at a fixed location, you have to call us up, tell us your plans, tell us what you plan on building, how much power you plan on using, where you plan on building it. And if we think that it's going to get in the way of our observations here, we can either say, no, you can't build that, which we almost never do, because we want people to be friends with us. or number 2, we can say these are the modifications that you have to make to your plan. And then once you get to West Virginia, we have a little bit more state restrictions that protect the observatory, and then Pocahontas County has given us a 10-mile radius around the Green Bank telescope, where we can say no Wi-Fi, no Bluetooth, no microwaves, nothing. I live within that 10-mile radius, so I have a cell phone, but I have to use an Ethernet cable to get any internet. So I have a little Ethernet cable that is hooked up to my phone, and oh, these are my bunnies. And this is how I yell at people on Twitter. Oh, I just knocked over my peanut butter. This is one of my favorite pictures. This is the Green Bank Observatory circa 58, 59. We had 3 telescopes. I'm sort of cheating. You can see this is the 85 one in the background, but ignore that. Right here we have what's called the sugar scoop. It was a feed horn. Here we have the 12 meter. And here we have the 12 foot and the 20 foot, not the 20 meter, excuse me. So I've got A, B, and C. 2 of these telescopes were used to look for interference from the surrounding community, and one of them was used to look at atmospheric conditions. So put in the chat A, B, or C, which one, using context clues, which one do you think is doing the atmospheric studies? You can send them to me personally if you don't want to be wrong in front of your colleagues. It's okay. Is my chat broken, or are people actually not sending anything?
We've got a bunch of A's.
Oh, we got a bunch of A's, really? Now, when you're looking at A, for the sugar scoop, you'll see it's pointed at the ground. Let me see if I can pull up my, no, I can't do that.
And a couple B's.
A couple B's, there we go. Oh, that's not what I wanted to do. I just wanted to look at the chat. Okay, whatever. So one of these telescopes is pointing at the sky. So that's the one doing the atmospheric test, and the other ones are pointing at the ground. So that's the one, those 2 are the ones looking at interference from the community. This is Green Bank now. Got a couple telescopes. We've got Grote Reber. We've got the GBT. Let me move your faces over. We have, this is the 140 foot, 45 foot. Right here is the Jansky Lab, named after Carl Jansky. Ever heard of him? You should have if you were paying attention. Right here, we've got the Science Center. That's where I am right now. I'm actually right here if you want to come say hi to me. So we've come a long way, I would say. We've got at least half a dozen big telescopes on site, and then a whole bunch of little tiny ones that are for different smaller research projects. So we went from 3 tiny telescopes to a whole bunch of big ones. Pretty nice. So this is the 85-1. Nobody calls it that. It's called the Tatel telescope, named after Howard E. Tatel, who was the engineer behind most of the telescope, especially the gearing system right here. He died before the telescope could be completed, so we named it after him so we wouldn't haunt it. We call telescopes by their diameter, not by their height. So it is 85 feet from one side of the telescope to the other. It is not 85 feet tall. This is another one of my pet peeves. If you're wondering how big it is, this is a 1-story building. that is the control room of the 85-1. Here we have the OG original gangster Frank Drake. Dr. Frank Drake, excuse me. He, in this picture actually, he is looking for aliens. This is Project Ozma, which was the first SETI project ever. In 1960, Dr. Frank Drake got $1,000 to look for aliens. He did not find any aliens. He was searching the spectra of 2 stars. He did find a top secret plane that the Navy was testing, and he was very excited about it because he thought it was aliens. However, it wasn't. It was spy stuff. He was not allowed to tell that story until very long after 1960, but there you go. This is the Little Bighorn. So every day, this funky looking feed horn, you can tell this tiny guy here, was pointing at 30 degrees. And every day it would take an observation of Cassiopeia A, which is one of the brightest radio sources in the sky, in the northern hemisphere. And this would be used to calibrate the 85-1. Now, this is actually in my backyard right now. It is no longer in zone 1, or the zone where you're not allowed to have any phones on. So I took some pictures of it for you guys now. It's a little decrepit because we no longer use it. We have better ways of calibrating our telescopes, but it is definitely a little creepy. I did not know what it was. This is another thing that you should not put your body into. I don't think anyone has ever done that, but it remains a concern. As you can see, we have some keep out signs here. So I'm just taking you guys through most of the tour, but also I feel bad that you won't be going on the real tour. So you're getting to see some stuff that you wouldn't get to see otherwise. So the insides of some of the control rooms and that sort of thing. Here we have the Green Bank Interferometer. Now, an interferometer is a group of telescopes that work together to simulate a larger dish. So the Green Bank Interferometer was not the first interferometer. It wasn't but it was one of the best. It was the first good one. So here we have the 85-1 off in the distance, that Tatel telescope that we talked about. And then we have, annoyingly, the 85-3 and the 85-2. I've never understood that. It's a little annoying. But these 3 telescopes would work together to simulate a larger dish. And this was actually the prototype for larger arrays like the VLA in Socorro, New Mexico, right here. Some of you might be working there, and ALMA in Atacama, Chile. So once we had sort of figured out how to get these 3 telescopes working together, we wanted to see how far apart we could get telescopes to do their thing. So we built this. This is a weird looking thing. It's the 42-foot telescope. And what we would do is we would fold this thing up like a colander, stick it on the back of somebody's truck, and drive it someplace. See if we could get it to work with the GBI. See if we could get any good data. That works. Drive it a little bit farther. Keep driving it farther. See how far away we can get telescopes to work together. Currently, the Green Bank telescope is part of the VLBI, the Very Long Baseline Interferometer, which has observatories from Hawaii to Puerto Rico. And each of these telescopes can work together to form a baseline that simulates a radio telescope the size of the planet Earth, which is crazy, and I love it. But it all started with the GBI at Green Bay. The 42 foot was not super well built, and taken around the mountains on the back of a pickup truck is not good for a telescope. So it lasted a good 10 years, 10, 20 years, 10 years. And then we needed to get a new one. So we gave that 42 foot to Cornell to work as an interferometer with Arecibo. And then we got this one. This is the 45 foot telescope. Now the 45 foot telescope was very lucky because it became part of the GBI in 1973. The Green Bank interferometer, the GBI, discovered Sagittarius A star in 1974. So the 42 foot did all the work and the 45 foot got all the credit. I feel sort of bad for it. But yeah, the Green Bank interferometer did discover or get the data for the supermassive black hole at the center of our Milky Way galaxy. It's very exciting. This is the best telescope on site because this is the telescope I work with the most. This is the 40 foot. The 40 foot telescope is a transit telescope, which means it can only move north to south. It cannot move east to west. Why don't we need a telescope to move east to west? Earth does it for us. Very good. So if I want to look at an object over here and I can only point up and down like this, all I have to do is wait a couple hours until it rises high enough in the sky to where it transits, transit telescope, and then you can point at it. If you miss your object, when is the next time you can observe it? Oh, and I figured out how to do the chat. Lulu Agazi. Oh, you're from Spot. Hi, Lulu. I've emailed you a couple times. Welcome. So 24 hours, Joseph has the more correct answer, 23 hours, 56 minutes. So Lulu was answering in a solar day, which is when the sun is in the same place in the sky. And Joseph was answering in the celestial sphere. So when Sagittarius A star or any given point on the celestial sphere is in the same place in the sky. So Lulu, if you're looking at the sun, you are correct. Joseph, if you're looking at Sagittarius A star, Cassia, any of those other objects, you are correct. Good job, guys. This is the interior of the 40 foot telescope. It underwent a deep clean with yours truly. So it's not quite as messy anymore. It still sort of looks like this though. Here we have Sue-Ann Heatherly, my boss. She gave you your 20-meter talk the other day. And this telescope is now a teaching telescope. So we have thousands of students, 5th grade and older, come visit us for the day. And they get to learn how to use this telescope. They get to learn how to use an old-fashioned chart recorder. And they can manually move the telescope. It's a whole lot of fun. I really like it. This is why it's the best telescope. Here's the 140-foot telescope. If you are working with this telescope, you will probably refer to it as the 43-meter. As I think Will was saying in the chat, we call it the 140-foot because it was built 140 feet. I think they originally wanted it to be in the metric system, but we were trying to get like American government money, so we decided that it was going to be American imperial. There's some drama behind that. There was a lot of drama with this telescope. It took way too long to get built. One of the reasons is that the guy who designed it decided that he could just like change how far the dish moved without changing anything else. And if anyone knows anything about like physics or logic or statics or, you know, anything like that, you know that you can't just tip something all the way over and expect it to not fall over. So we had to fire him, hire a new company. It's a little obvious, but the second company that we hired was actually a boating company, a company that built boats. But they built us this telescope. It's a great telescope. It is an equatorial or polar mount. So this is two different sides of the telescope, but you see this polar mount right here, which is at 38.3 degrees. 38.3 degrees. Coincidentally, by the way, we are at 38.3 degrees latitude here at Green Bank. So this polar mount is pointing directly at Polaris, our North Star. Now this is helpful, sort of, because if you want to track an object across the sky, you only have to move one of your axes instead of two on a polar mount. This is not good because this is a giant telescope. And when you try to build a polar mount, your giant telescope is at a 38.3 degree angle, which is a little difficult to figure out the counterweights for. Still, we got it built. It was working most recently on the Radio Astron project. So when the Radio Astron satellite was over Russia, they would downlink it. And then when it was over our side of the Earth, we would downlink it and so on. That project ended last year because they lost the satellite. It actually lasted for 9 years longer than they were expecting it to. So we're not super mad about that. But if anyone has any fun projects that they want to do with the 140 foot, hit us up because it's not doing much right now. It's looking cute, but that's about it. The 140 foot telescope is home to, at the time, the largest hydrostatic ball bearing in the world, 17.5 feet wide. It is giant, weighs 167 tons. I do not have that memorized. It just says it right here. It's very large. It is no longer the largest. However, the Dutch made a storm surge barrier in the 90s, and they couldn't just make one bigger hydrostatic ball bearing. They had to make two. So now we're number 3. A little bit salty about that, but that's okay. And then here is the control room for the 140 foot telescope. One of the fun things about the 140 foot is it was built during the height of the Cold War. So it actually has a fallout shelter in its basement. The fallout shelter can hold 30 people, and it has no food, water, oxygen, blankets, but anything that you might need during a fallout shelter situation, it's not there. And the Green Bank Observatory employs about 100 people. So it can't hold any of us, all of us, but you know, it's there if you need it.
Lucy, there was a question asking, why is the 140 foot telescope not as active anymore?
Because we have the GBT, to be honest. We're looking for another project for it. One of the thoughts is we might it might be used for bistatic radar if we get that radar on the GBT or maybe on the 140 foot. I'm not sure. I'm not a radar expert. Ask Amber Bonzel about that. But yeah, we don't really have any projects for it right now. I think we're in talks with some people, but that's not my department. I just tell people what it's currently doing, and currently it's not doing anything. One of the fun things, another fun thing about the hydrostatic ball bearing is that the word hydro would have you think that it's covered in water, but it's actually covered in a highly flammable fluid, which can burst into flames at any second, apparently. So this telescope, so the ball bearing is right here. had to have a very advanced, for the time, fire suppression system. So if you're in this control room and you hear like a fire alarm sort of sound go off, you have about 10 seconds to get out of the control room before the entire thing is CO2 and not oxygen. It gives me a little bit of anxiety whenever I go in there, even though it's been up for 50 years and it has not caught into flames, but it's a fun thing to do. This is the 300-foot telescope. It's a cute little one. Jay talked a lot about this, so I'm not going to get into it. This is a 2-story building, if you were wondering how big it was. Here is the control room for the 300. This also ended up being the control room for the GBI, the Green Bank Interferometer. So this was the 300 foot at in the afternoon of November 15th, 1988, and that was November 16th, 1988. One of our operators was in the building at 9:43 when this collapsed. He had just come out of the bathroom and it collapsed on the bathroom. So he was okay. He actually still works for us. He's one of our longest serving telescope operators. We had a little bit of a PR problem after this, just a little bit. But Senator Robert C. Byrd, head of the Senate Appropriations Committee from West Virginia, called us up and asked us the next day, how much money do you need to build a new telescope? The director at the time said $75 million, and Senator Robert C. Byrd got us $75 million. This is my favorite picture ever. It reminds me sort of those pictures of the cat stuck in the blinds. It's like, this was the original design for the GBT, and it's a bit of a mess, but you know, we're working on it. And then this is a great video. Over 10 years from 1990 to 2000, every day somebody took a picture of the GBT's construction site. So planning started in 1988. Construction started in 1990. This was 2000. First light was 2001. Here's the GBT. Oh, that's not what I wanted. Here's the GBT now. It is 485 feet tall. That's 30 feet taller than the Great Pyramid of Giza. It weighs 16 million pounds and can rotate 360 degrees in 9.5 minutes. It is the third largest moving structure on land. The second is some strip mining giant thing in Australia, and then the Germans did something. I forget what they did. Nobody really cares about them. So here we have the Green Bank telescope. It is a partially parabolic dish. Ryan just he just went like this because I said that we don't care about the Germans, and I saw that, but it's okay. How this telescope works is radio waves come down from space and they bounce off of the dish to this subreflector, which then bounces the radio waves into the receiving room right here. These tiny little trucks are about 3 people high. And it moves left to right along that sort of circular track. And then there is this U-shaped horseshoe that will move it up and down. It has 2 elevators. One is on the other side, but it goes from here to here. You walk across the catwalk if you need to get up to the receiver room, and then there's a second elevator that will take you up to the receiver room. You have to go higher than the receiver room. You have to go through special ropes training. Now, I am going to open up the chat and somebody say something if you have not heard of the double slit experiment. Somebody just put like a sad face or something. You have not heard of the double slit experiment. Very good. So here we have a beautiful little radio galaxy. And because it's so far away, the waves that come to us from it are sort of in these parallel lines, right? Now, in a normal dish, this is going to cause a bit of a problem. And this is the lobes issue that we were talking about earlier. So if you have your receiver in front of your dish, that's going to cause interference and you're going to get these sort of weird lobes along the sides of your dish. However, if you were to move the receiving arm out of the way, you just get a whole bunch of straight lines. Now, this is a problem because if you were to just build a telescope that looks like this, all of the radio waves would still bounce off into the focal point here. So what we did, let me get another color, what the design of the GBT is basically we only built this part of the parabola and we still had the receiving room here. So when we receive these signals, we still have these straight lines, but they're going to bounce still into the receiver. Does anyone have any questions about that? Because that's a little difficult to wrap your head around. Let me open up the chat. Or not. There you go. Bandwidth of the 140 foot. Ryan answered that. Okay. So the GBT is a very unique design because of this sort of clam shape of the 40 foot. The GBT, I don't know why I said 40 foot. And that caused a bit of an issue because, if I can go back, this arm creates like a bit of a problem because it's off kilter, right? So you want your moving objects to be as symmetrical as possible. So we actually have a bunch of counterweights right here along the sort of horseshoe shape that's about the same weight as the arm, and that's going to balance it out. Now, when the GBT was being built, it was designed by some very smart people who I love and respect. However, they did not add in the weight of the welding materials into the total weight of the telescope. So the GBT, so Autumn, let me finish this and then I'll go back to that. So when the telescope was built, it ended up weighing a couple million pounds more than it was supposed to. So we actually had to replace the track in, I think, 2007. I might be wrong about that, with Teflon. because the weight of the telescope was so heavy that it was scraping away at the metal that the track was made of. Now, you might wonder, Lucy, how did you measure the weight of the GBT? How do you know that it's 16 million pounds? Well, we jacked it up like a car. So we went to this little truck. I have a better picture of that. We jacked this whole thing up, weighed it, said, oh, that's about 4,000 pounds. Went to the next one, weighed that, that's about 4,000 pounds. Did that for every wheel or every truck, 16 million pounds. I said 1,000, I didn't mean to. Let me pull up that question in the chat. Yeah, so the black gray wall, I am going the wrong direction. So this is the, so this right here would be the dish, right? So we get these lobes of interference or on the dish of the telescope. And there was another question that I saw, but my chat doesn't know how to. So the reflected waves interfere with the incoming waves. I'm not sure about that. Ryan or Will or Jim, do you know the answer to that? Laura's question?
I would say that one thing that you see in other radio telescopes that have struts that support the receiver is that you do get reflections of light in between the strut and the surface called standing waves, and that does affect the quality of your images. That's why the GBT has so much better performance than the Effelsberg telescope in Germany, even though they are of similar sizes. That's one of the reasons.
I think she was asking why the interference coming from the waves that are coming in and then bouncing off the dish. Does that make sense?
Yes, I wouldn't think that there would be interference from that. The only thing I could think of is if there were reflections.
Okay.
In there.
Thank you, Dr. Will. So this is the receiver room of the GBT. It can hold a whole bunch of receivers at once. So if you want to do an X-band observation, for example, we can move the turrets around like a merry-go-round so that the X-band is in position. And then the next observation is K-band. We can move the receivers around so that Ka band is in position. And this way, we don't have to go up to the telescope and change out the receivers every time we want to look at a new wavelength. Now, the wavelength of the observation you want to do is going to be proportional to how big the receiver has to be. So if we have, so a tiny little receiver like this one is going to be looking at a smaller wave than a giant one like this. And if we're trying to do like a gigahertz or something, there are some receivers that cannot fit in the receiver room. So we actually have a boom that'll come out. I don't have a picture of this, so I'm doing my weird hand gesture. A boom that'll hop out in front of the subreflector that has the largest size of the, oh, Will, yeah? You saying something? Go.
So continue what you're saying, and then there's a question.
Yeah, okay. So so we have this largest receiver, and we can swing it out in front of the subreflector so we don't have to fit a giant receiver into a tiny receiver room. Are those electronics in the picture the same electronics we talked about yesterday? I don't know what you talked about yesterday. Ryan, do you want to help out?
Yeah, so what you're basically seeing in this picture is the back part of the receiver assembly on the left-hand side. On the right-hand side, you're seeing the tops of the feed horns. So these are kind of these conical shaped pieces that help to convert the incoming radiation into something that can then kind of travel via electrical cables, coaxial cables. And on the left-hand side, the back part is the cryogenic components and the refrigerators and the cryogenic pumps that keep the amplifiers cold. So the actual amplifier circuitry and some bandpass filters are going to be in there, along with, there's also in this picture local oscillators and mixers, but it's all kind of a jumble of cables and other things there.
Are there any diffusers on the GBT?
I'm not sure what you mean by diffusers, actually.
I'm assuming they're things that diffuse other things, but I don't know the answer to that. So you guys can figure that one out in the chat. Here's one of the tracks of the GBT. Nobody has ever gotten run over by it. We did have one close call though. He is fine, though he no longer has a job at the Green Bank Observatory. This is the 20-meter telescope that you were that you're going to be working on. I think that it's actually off right now to do some cryogenic maintenance, but it should be back on by tonight. Someone knock on wood, there isn't any wood around me. So the 20-meter is the only telescope on site that's named using the metric system because it was not built by Green Bank Observatory. It was actually built by the Navy. 1994, the Navy called us up, asked us if they could use the site and the quiet zone to calibrate their brand new global positioning system. Ever heard of it? So this telescope was used to track continental drift and precession, which is the wobble of the Earth on its axis, for about 10, 15 years until they were done with that GPS project. And then they gave it to us. So now it's mostly a teaching telescope. It does some work with the Pulsar Search Collaboratory. So it's looking for pulsars a whole lot. It's a great little telescope, except for the fact that it hasn't worked for the past 2 months and it's made my life very difficult. And now I'm going to take you into some of the fun different places in the observatory, just because nobody ever gets to see these and I think they're really cool. So this is the anechoic chamber. Ana means not, coic it comes from the same word as choir, which makes noise, so not noisy, quiet chamber. Basically what this is we can put a new device over here, and then we have an antenna on this side. We can plug it in and see how much interference it gives off. So when we wanted to get a brand new water fountain in the Science Center, we had to build it or buy it, bring it to the anechoic chamber, plug it in. I don't know if they hooked it up to any water or not. I'm not sure if that was a problem. And see if the amount of interference it gave off would be a problem for the GBT. It was just under the limit, apparently. So we do have a brand new water filter, filtered water fountain in the Science Center, which is very exciting. But yeah, I just love, it looks like some weird medieval torture room. It's one of my favorite things to look at. I love it. This is Chuck in Emmett. Emmett is our electromagnetic interference tracking truck. So we've got this big old pickup truck that has some antennae on it, and he can go out with all of his spectrometers and all of his fun stuff and find sources of interference. So if, for example, Frontier Communications has a downed power line or a down data line, that is causing interference, Chuck can go out and find it and then call Frontier and try to get them to fix it. The fixing it part is the difficult part. The finding it part is the easier part, considering we have this fun little Ghostbusters truck. Here we have the machine shop. All of our machinery and all of our electronics are built on site. Even these lovely fluorescent lights that make my skin just look so good in the Science Center have to be modified because of the interference problem. So all of these fluorescent lights in the Science Center have little tiny Faraday cages in them to lessen the amount of interference that comes from those lights. A whole lot of stuff is built here. It's a really fun place. Don't allow me in there because they think I'm going to break something or hurt myself, and that's probably a good idea. And then this is very exciting. This is our brand new, as of this year, array for the CHIME experiment, which is the Canadian Hydrogen Intensity Mapping Experiment. I think, oh, I got a thumbs up from Will, so that was correct. This is basically creating an interferometer with a telescope in British Columbia called CHIME, looking for fast radio bursts. And fast radio bursts are one of my favorite things in the world because we don't know what they are, so I can say they might be aliens. They're probably not aliens, but you know. So we have all these like little tiny cheap telescopes that we're trying to get up and running to work with the CHIME telescope to create an interferometer. Now the CHIME telescope, oh, I am out of time, so I'm going to not talk about that. You can Google it if you'd like.
Okay, thanks. Thank you for sticking to your time. That was great. Are there any other questions for Lucy?
I do want to mention that that lobe sort of reflecting problem is going to be a problem on sort of any telescope that has a subreflector. So even the normal telescope, even like an optical telescope that you have at home, is going to have sort of, when you're looking at a telescope, at a star or a point source from a telescope, and you see that sort of a cross shape, that's a similar effect to what we're talking about here. The most expensive telescope at Green Bank Observatory was the GBT. The GBT cost $75 million to build and approximately $25 million in the ensuing 20 years to upgrade and maintain. So it's about a $100 million telescope. Those last dishes were part of CHIME, yes. Here, they might be similar to HERAX prototype dishes. I don't know anything about that. I'm just gonna look through the chat and see if there's, yes, we do have microwaves in Faraday cages. The microwaves give off a whole lot of interference. So we've got three or four on site that our lead electronics engineer had a project where she designed a very fancy metal box that you can open, put your food in, close the microwave, close the box, and then the microwave will not start until the box is locked, which is very exciting. I just use a toaster oven because I'm a simp. I don't know. One new message. Oh, that's Ryan. I'm just looking through this chat and see if I missed anything. So we use feet for the diameter because we're Americans. God bless America. If you guys have any questions, you can unmute yourself and ask them. But Bandwidth, you answered that.
Yeah, I think we fielded all of them. And I also put
Okay.
a response into Casey's question about the diffuser because clarified what we meant by that. There is
Yeah.
something kind of similar which we use, attenuators. Those are downstream
Yeah.
of the IF path.
I know that Chime is trying to build a second Chime next to the 85.1. We're not sure if that's going to happen yet. But if you go, Jay talked a little bit about Chime, but it's the funky looking telescope that it looks like a whole bunch of like skateboard ramps all put together. And the idea behind that is you want to be looking at a large swath of the sky at any given point, because things like fast radio bursts, by the time you move your telescope to point at it, it's gone. So that's sort of the idea behind it. I'm not sure where that project is right now, considering the guy who does the who was doing the environmental report is in was John, and John is working in New Mexico now. So I'm not sure.
Yeah, I think that project is still moving ahead.
Oh, that's good.
as
That's
best as things
exciting.
can during these times.
Yeah.
So, okay. If there aren't any other questions, then thank you very much, Lucy.
Yeah, I'm gonna put my email in the chat if
Great.
anyone wants to talk about outreach or I can't talk and type at the same time. If anyone wants to talk about outreach or has any questions that they didn't want to ask in front of people or anything, or just wants to say hi because I'm lonely because I live in Green Bay. I'm also on the Slack whatever, but I've never used Slack before, so email me or friend me on Facebook, because again, I don't have many friends. Will and Ryan are my friends, but they are both not in Green Bank at the moment, and I wouldn't be able to see them if they were. So.
All right, thanks, Lucy.
I can take a hint.
We miss you. All right.